Welcome to the Pegasus System, a new system for learning to create accurate Lewis structures. The simplest molecule that we can represent in Lewis theory is H2, diatomic molecule of hydrogen gas. To come up with the appropriate structure, we notice that we have two hydrogen atoms, and we recall that each hydrogen atom has exactly one valence electron. That's one electron in general. So, in the entire molecule, the total number of electrons is going to be 2, one for each. And we are reminded of this by looking at the cards. The cards have a group number on there. It's in the first group, and M is for main, so it's in the main group. It's not a transition metal, for example. And for group 1, it's going to have one valence electron. So for the entire molecule, we have 2 electrons. And here we have our pegs for the Pegasus system, which are push pins, and we have 1 pin for each valence electron. So long as we can distribute the valence electrons within the rules of the Lewis system, we know that we have, or are likely to have, a valid structure. So we have our 2 electrons. Now we recall that each individual hydrogen atom is happy, so to speak, when it has 2 electrons. So we call this the Duet rule. And the reason why this works is that in the 1s orbital for hydrogen, it can hold a maximum of 2 electrons. So the way the system accounts for it is we notice that if we have these 2 holes, okay, we can overlap them in such a way that when we put an electron in, our push pin, it simultaneously is present in both of the holes. There we go. So we have a hole filled up with 1 electron. Now we notice that we have 1 more hole to fill. So now we put the second electron in here. And we see that when we share 2 electrons between the 2 hydrogen atoms, we've satisfied the Duet rule, basically the desires of each hydrogen atom to have 2 electrons. So the way we can achieve this, to have each of the 2 atoms have 2 electrons, is for them to share. Now, one of the features of this system that is useful is that there is no possible way for any hydrogen atom to have more than 2 electrons because there's simply not enough holes. There are not any holes there. One of the most common mistakes that students will make is to put more than 2 dots, more than 2 electrons, around a particular hydrogen atom. And within this system, because of the way the cards are designed, that is simply impossible. One thing we can notice also is in this system is that these holes are in a region that is shaded gray. The significance of that will be clear later on, but for the time being is we realize that any of the gray areas need to be filled. If we have a region that isn't shaded gray, that is shaded white, for example, that is an optional, which we can put electrons there, but they're not required. Now, one additional feature that we can do in the system, which isn't required, but it can be useful to see, is we can color code the electrons. So, for example, let me replace one of the red electrons with a blue electron. So put that in there. Now, there are 2 aspects to this. One is it's just simply more colorful, which is nice. There's no great significance to red and blue, except that I'm from the United States and our national colors are red, white, and blue. So this will also be appropriate for citizens of the United Kingdom, France, the Russian Federation, for example. But other than that, we can also think of one of the colors, red for example, as giving an up electron, and the blue pin being a down electron. So here we've accounted for the Pauli exclusion principle, that within a single orbital we can stick 2 electrons in there so long as they have opposite spins, as long as one is an up spin and one is a down spin. So this introduces us to the basic system of the Pegasus system for the simplest possible molecule, H2. The next compound that we would like to investigate is water, H2O. And we recall that in a molecule of water, we have 2 hydrogen atoms and 1 oxygen atom. So we see an interesting feature right away of elements like oxygen. Oxygen isn't like hydrogen. Hydrogen wants to satisfy the Duet rule and fill up the 2 holes that are next to it. Oxygen, on the other hand, has 8 of these holes. So therefore, it wants 8 electrons, and we say that it satisfies the octet rule. This octet rule will be important for all the elements on the second row of the periodic table. To help us remind us that this is true, we have 8 holes. And the 4 pairs of holes are shaded gray, which reminds us that we're required to fill up those holes. Now, the next thing we have to keep track of is how many electrons are present in this molecule. Within the Lewis-Langmuir model, we are interested in the number of valence electrons, not the total number of electrons. For any particular atom, we can divide the electrons up into core electrons, which are very close to the nucleus, and valence electrons, which are involved in bonding, in making compounds. So, again, to remind us of exactly how many valence electrons each element has, we have printed on the card a group number. And this reminds us, for example, group 6M, that oxygen has 6 valence electrons. Each of the hydrogens, reminds us, has 1. So if we add up 6 plus 1 plus 1, we should have a total of 8 valence electrons that we need to allocate in this molecule. And I've already counted them out up here. So I have 4 of the blue and 4 of the red. So we have a total of 8 valence electrons. So the key here is I have to simultaneously satisfy the desires of the 2 hydrogen atoms to each have 2 electrons, and the oxygen atom to have 8. So the way that I can do that is by sharing a pair of electrons between hydrogen and oxygen over here. So let me put those in. So I have 1 blue and 1 red. So for the time being, this particular hydrogen atom is happy. It has allocated, it's satisfied the Duet rule. So now let's see if I can satisfy the other hydrogen atom. So I can do this by sliding these holes so they're lined up, and in this way the electrons are shared between the oxygen and the hydrogen atom. Let's do that. So I satisfied the Duet rule for each of the hydrogen atoms. Now, these electrons, which are shared between 2 different atoms, we call bonding electrons. These essentially are the glue that holds 2 different atoms together in a compound. But we still have 4 more electrons that we need to allocate, and we notice that oxygen needs 4 more electrons to satisfy the octet rule. So let's see if we can allocate those electrons in such a way as to satisfy the octet rule for oxygen. Let's see if we do that. So if we put these electrons here, for example, we notice that we've used up all the electrons. It's very important that we don't lose any of the electrons, because electrons are a type of particle called a fermion, and we are not allowed to create or destroy fermions. So we can't just throw electrons away, not allowed to do that. So we notice that we started with 8 electrons, and we've allocated all 8. That's good. And that's one of the features of this system, is that so long as you don't accidentally drop the electrons, you are able to keep track of how many electrons you started with and how many electrons need to be allocated. So, and we've satisfied the Duet rule for each of the hydrogens, and we satisfied the octet rule for oxygen. And we noticed something special about oxygen that we didn't see before. We have 2 different types of electrons. We have electrons which are shared between 2 atoms, so these 2 electrons are shared between hydrogen and oxygen. So again, we call those bonding electrons. Over here we have hydrogen and oxygen. We share 2 electrons. So again, we have 2 more bonding electrons. We can call them a bonding pair. And then we have 2 other pairs. We have a pair up here and a pair up there, and these are considered to be just sitting on the oxygen, but not shared with another atom. We call these things lone pairs. And lone is L-O-N-E, meaning they're by themselves. They're only on one atom as opposed to being shared between two. Later on, we'll be able to see that we can even use the word lone and use the homonym L-O-A-N, and that will have a certain significance. But for the time being, this is our first triatomic molecule, and our first molecule where we have both bonding pairs and lone pairs. The next molecule that we would like to draw a structure for is the compound called ammonia. And ammonia has the chemical formula NH3. It has 1 nitrogen atom and 3 hydrogen atoms. So in this case, again, we recall that each hydrogen atom has 1 valence electron. And nitrogen is in group 5, so nitrogen has 5 valence electrons. So this is similar to the water system in that, again, we are trying to allocate 8 valence electrons. It is very useful when you're learning how to make Lewis structures to keep track of the total number of valence electrons. You'll notice that there are a large number of patterns which emerge based upon how many valence electrons you have in your system. So here we have another 8 valence electron system. And we have our 8 valence electrons as our pushpins. So let's see if we can allocate the electrons first to satisfy the hydrogen's Duet rule, and then see if we can satisfy the Octet rule for nitrogen, the same way that we did for oxygen. Let's see. Okay, so we were able to allocate electrons to satisfy the Duet rule for each of the 3 hydrogens. But we noticed 2 things. One is that we have 2 electrons left over, and nitrogen only has 6 electrons, and it needs 2 more, and we can tell because there's 2 holes in this gray region which are unfilled. So we can actually satisfy both those problems at the same time by putting these 2 electrons into the diagram. So we see we're able to satisfy the Duet rule, satisfy the Octet rule, and we don't have any electrons left over. When we're able to do all those things, in general, we're going to have a valid structure. This will be a legitimate molecule that we would expect to exist. If we end up with a situation, if you tried to do this and we took one of the hydrogens off, we would notice that we wouldn't have enough electrons to satisfy the Octet rule for nitrogen, so you would imagine that particular molecule would be unstable and or not exist at all. Now here we have 3 bonding pairs. We have a bonding pair, bonding pair, bonding pair, and we have 1 lone pair. Now we'll learn later in your chemistry courses that this lone pair of nitrogen is very commonly associated with the fact that nitrogen is a base. In general, these lone pairs, particularly lone pairs on nitrogen or oxygen, are very commonly involved in a property which we call basicity. But for the time being, we're able to make a valid structure here. Next, we would like to find a Lewis structure for the compound hydrogen fluoride, which is a gas, and when this gas is dissolved in water, we call it hydrofluoric acid. It's an important reagent because it has the property that it will etch through glass and eat through bone and concrete. So it's a very corrosive material. So we see the hydrogen has one valence electron. Fluorine is in group 7. It's in a group of elements which we call the halogens, the salt formers, and they have 7 valence electrons each. So in this particular molecule, we'll have a total of 8 valence electrons that we need to allocate to come up with a legitimate Lewis structure. So let's see if we can do that. First, we use 2 electrons to make a bonding pair between hydrogen and fluorine. And we see now we've satisfied the duet rule for hydrogen. But fluorine needs 6 more electrons to satisfy its octet rule. And turns out we have 6 more electrons. So let's put them in. And there we go. We were able to allocate our 8 electrons. We have 1 bonding pair between hydrogen and fluorine, and we have 3 lone pairs on fluorine. So since we're able to satisfy both the duet rule and the octet rule, and use up all our electrons without losing any, we believe this to have a valid structure, and it turns out that this is the valid structure for hydrogen fluoride. For our last 8 electron system, we're going to look at a compound called methane, which is often called methane in Great Britain. The chemical formula for this compound is CH4. If you heat your house with natural gas, this is the actual material that is burning to generate heat. So this is a hydrocarbon gas. It's very widely used for energy generation. So here we have 4 hydrogen atoms. Each hydrogen atom contributes 1 valence electron to the system. Carbon is in group 4, so carbon will contribute 4 valence electrons. Carbon, we'll see later on, is the key ingredient in the widest possible range of compounds in a field called organic chemistry. So the chemical compounds of carbon are extremely important for both organic chemistry and the chemistry of living systems, which we call biochemistry. So let's see if we can generate a valid Lewis structure for this very important compound, methane. So let's see first if we can allocate our electrons to satisfy the duet rule for the hydrogen atoms that are in the molecule. There's 1. And there we go. We're able to allocate all the 8 electrons. Not only were we able to satisfy the duet rule for the 4 hydrogens, but in the process, we satisfied the octet rule for carbon as well. So we see this is a important compound that is a valid Lewis structure because we're able to satisfy the duet rule, the octet rule, and maintain the correct number of electrons. We haven't violated the law of conservation of charge for the fermions. Now we notice that in this particular molecule, we have 4 bonding pairs and there are no lone pairs. So as we go from hydrogen fluoride, that has 3 lone pairs, water has 2 lone pairs, ammonia has 1 lone pair, and then in the sequence, methane has 0 lone pairs.